encounter while monitoring sites in general. After that, we will see what wireless technologies are currently available in the market. Then we will talk about Worldsensing monitoring solution, and then we will see compatibilities of this solution with some sensors of interest in this field and some use cases. After that, Víctor will jump in. He will explain the use of tilt meters. He will also talk about the different errors commonly associated with these sensors. He will also explain the use of this tilt meter in event detection state, and we'll finish the presentation explaining one particular use case. Okay. Tracing back the evolution of instrumentation and monitoring for applications in geotechnics and in hydraulic engineering, we find that back in the 30s, the vibrating wire monitoring technique was developed. It was later on, around the 70s, that this manual task evolved to become an automated one with the use of data loggers. So the idea was to connect data loggers to a central unit from where the data was transferred and where the data was also recorded. It was just recently, in the past years, that the vibrating the wireless solutions arrived into this field. So if we look at this evolution, we can understand this as a natural response to the different challenges that we face while monitoring sites. It's obvious that collecting readings manually has some limitations. For example, when it comes to the volume of data and accessibility to that data, that other solutions, automated solutions don't have. It also has involved a higher risk of human error, and a higher risk of data tampering. And of course, it's not easy to adjust this instrumentation and monitoring to the constant changes happening on site. In any case, I have to say that this manual collection of readings is still a task that is done. Particularly for those sites that doesn't cover like large areas, or where there is not a real need to collect readings so frequently, then it's common practice. And also when there is also a high risk of having in place inclinometers on site, because they can get really damaged. Moving on, if we focus on the cable solution, the main drawback here is that it requires certain programming skills that not everyone has in order to properly set up and configure the equipment. And also it's hard to adjust the solution to the quick changes happening on site. We have to think that this cable solution involves large amounts of cables that need to be laid down and need to be protected. For that reason, wireless seems to be the best choice in the majority of cases. Let's see now what wireless technologies we find. We can go, for example, for local area networks such as Zigbee, Bluetooth, or Wi-Fi, or for cellular connectivity solutions such as GCM, 4G. Another alternative are the low-power wide area network solutions that includes Sigfox, for example, or LoRa. LoRa stands for long range, and as its own name says, it has the advantages that the devices operating with this technology can communicate with each other, even if they are located at far distances, up to 15 kilometers, and even if there is not direct line of sight in between these sensors. This is a huge advantage as compared to local area network solutions, because these solutions don't achieve such long distances for communication purposes. Also, if we compare LoRa with cellular technologies, we have to say that LoRa has a much lower power consumption. That implies that the devices running on this technology can run on internal batteries that can last for years. Also, as compared to satellite to solutions not that use satellite modems. Well, LoRa is more economic technology in general. Well, I forgot to say, no, the main drawback of the LoRa, however, is that it has low data rate capacity. That means that is only capable of sending simple and small amounts of data packages at once. In any case, LoRa, because of all these properties, has become the de facto technology for all the IoT networks all over the world. So now let's see how Worldsensing solution works. This diagram corresponds to the CMT Cloud architecture or multi-gateway architecture. As we see here, the first thing to do is to connect the sensors to the wireless data loggers, unless we're talking about data loggers that have sensors already built in, so we don't need to do this external connection. Well, after that is done, we need to configure the system by using a mobile app in this case. Then once the sensors start collecting data, this data is stored in these data loggers and also transferred via radio waves to one or several gateways. Worldsensing technology relies on LoRa. So these radio data packages that arrive in these gateways are redirected by these devices towards an external data server, which is located in the cloud. We can have remote access to that data server by logging remotely using a web-based platform known as the Connectivity Management Tool, or CMT. Once we are inside the data server, we can set the system to automatically transfer that data recorded on the data server to be transferred to an external data server for data management visualization, for example. Imagine if we want to generate some graphs or create alarms, and so on. That can be done thanks to the different communications protocols implemented in the data server. I have to say this multi-gateway architecture is a convenient solution for those projects where due to they have to cover big areas, maybe with some physical obstacles or with difficult orography, for example, where we need to ensure all the data loggers scattered all over the site at least can communicate with one of these gateways. And it's also good to have redundancy, because we have to imagine that if one of the gateways fails, at least we will have one more gateway up and running to collect this data, so we won't miss any readings. There is, however, another alternative, which is the edge or single gateway architecture. This is very similar to the previous one, but as you can see in this diagram, it only operates with one gateway. And in this case, the data server is no longer located in the cloud. Is embedded in this device. This is a good solution for the majority of cases where we don't, as I have said before, this system allows communications between devices that are 15 kilometers apart. So in most cases, projects don't require to have more than one gateway deployed unless they want that redundancy. In some other cases, there is no other choice because the owner of this of the project is not well, for security reasons cannot operate cannot have a system operating online. Well, yeah, this is here we can see some of the functionalities that the connectivity management tool can offer to the users. Among some functionalities, the main ones I would say are listed here. No, we are able to check on the status of the gateways and on the status of the loggers, whether they are all okay, connected, and operating well. No? We can also download any sort of readings in CSV files. We can also apply some formulas, to convert raw data into data with proper engineering units. We can also change remotely, the sampling rate of the devices. Okay, now we're going to see what combination of load sensing devices and sensors we can make use of in order to monitor parameters linked to the triggering of slope instability, and also some other parameters that will tell us whether there is any movement or deformation already happening and at what rate it is happening. Precipitations and changes to the hydrogeological conditions are some of the parameters that can trigger instability on a slope. In general, the presence of water, what it does is it increases the weight of the ground. It also increases the ground saturation level. It can also cause the internal and external erosion of this ground, and in general, decreases the shear strength of the ground. It's for that reason that parameters like, for example, the pore water pressure or the phreatic level are commonly monitored in these scenarios. For that, it's usually the sensors that are usually employed are piezometers, vibrating wire piezometers, because vibrating wires are sensors are quite robust. So in this case, this sensor should be connected to vibrating wire data loggers. Also, for those areas with freeze and thaw cycles, it's also worth it to monitor the air and the ground temperature, and also the rainfall. In this case, the combination of these sensors could be connected to one the analog data logger. In general, the temperature sensors are designed to report analog output signals. And in the case of the rain gauge, some of them report pulse counters. These are output signals that can be read by this type of data logger. Some other parameters that are also commonly tracked in these scenarios are the soil moisture, the soil water potential, and also the probably snow level if there is snow. Usually, these sensors are also designed to report an analog output signal, so they should also be connected to an analog data logger. This is a use case. Okay, it's based in Germany. It's about an old mining area where lignite dedicated to the extraction of lignite deposits. This area has records of past landslide events, as we can see in this first image here. And landslide, the ground approach enter into the boundaries of this building, which was a former guest house, and severely damaged this building. Consequently, this building was abandoned. Actually, the entire area it's abandoned because there is still risk of landslides. For that reason, the Road Safety Authority requested to keep this location under monitoring. That's why 3 measure and shape arrays were installed. Shape arrays are short of in place inclinometers. Okay, place inclinometers are a chain of tilt meters, no? In this case, arranged in a vertical line. So these sensors allow us to compute, no, the lateral movement, the lateral displacement of the ground by, no, out of the tilt measurement by using these formulas shown in this other image, no, on the bottom, on the left hand side. By doing this, no, we can come up with soil profiles like the one, no, shown on the next image. I have to say these sensors are also good, no, for the determination of the shear plane, no, of potential landslides. So as I said before, no, in total, 3 of these shape arrays were installed, each of them connected to a digital logger. We can see some pictures of the final installation down here. On the left, on the right-hand side, sorry, we have some pictures related to the installation of the gateway. On top is an overview where, no, where the gateway was located. It was somewhere nearby these sensors and data loggers. And in this case, no, the gateway, which is shown in this, is this device, was powered, no, using an external solar kit in this case. This is another use case based, in this case, in Switzerland. Here, the main concern was, no, the stabilization and monitoring of this 120-meter high rock cliff. We cannot see at this picture, no, the first picture on the left hand side, no, but at down there, no, at the bottom of this cliff, there is a road and also a railway line. So the main concern was, no, to protect this area against potential rockfalls. For that, no, the preventive measures that were implemented were, no, the installation of nets, and also the installation of pre-stressed ground anchors. For that, as we can see on this image at the middle of the slide, no, it was necessary to make use of a scaffold and also to make use of a helicopter. So we can imagine, no, such a scenario, how convenient it can be, no, to have a wireless plug and play solution for monitoring purposes. In relation to the monitoring, some of these ground anchors, no, were monitored with load cells connected to analog data loggers, no, with the idea to see whether any further, no, preventive measures were needed. And also borehole extensometers were connected to analog data loggers were installed. We can see on this other image, no, on top on the right hand side, ahead of one of these borehole extensometers. Just above, we can see a schematic of this sensor. These sensors, in this case, no, there were 3 sensors. Each of them, no, located at the, well, measuring the relative displacement, no, of the ground with respect to the measuring head, no, at different lengths or depths. The displacement transducer are, in this case, located in the measuring head. So the idea was to see, no, this elongation, no, of the ground. Here we have a couple of charts. The one on top, no, belongs to some of these ground anchors, no, monitored with load cells. We see that over, no, this 4 months period of time, the readings were quite stable on this side. And in the graph just below, no, it corresponds to one of these borehole extensometers. In this case, we see like that in each one of these sensors, small movement was detected, no? On the right-hand side, we can see a close-up view of the layout of some of these instruments. The borehole extensometers are this corresponds to these 3 dots, no, shown here, no, in a row. here and here, well, all of this. And load cells installed onto these pre-stressed anchors were located, in this case, just down there. Okay, in this other use case, based in Slovenia, it was about another rock cliff. This rock cliff is massively fractured and also affected by large fault. This area has this rock consists of dolomites with intercalation of myelonites, and it has also past records of rockfall events. Actually, one of these rockfall events caused the closure of the road adjacent to this slope. We can see this road at this other image just below, in the center, in the middle of the slide, is this one. For that reason, the owner wanted to implement some preventive measures. They, for example, got removed the loose material, and also got installed nets and nails onto this rock cliff. And in terms of monitoring, they requested to get 2 till meters installed at 2 specific locations. We can see again on this this image in the middle of the slide. We can see it's very tiny, but there are 2 climbers doing this job. On the right-hand side, I have included a picture which is quite representative of what the installation of these till meters looks like, although this picture doesn't belong to this, doesn't correspond to this site, but I think it's quite representative. Besides these till meters, the owner wanted to get installed 4 draw wire extensor meters. The wire extensor meters are part of track meters family, connected to analog loggers. We can see on these 2 images below how the team were installing these sensors. And just recently, this monitoring system was complemented with the installation of a laser distance meter, which is pointing at the top of this slope. This laser distance meter is attached at the wall adjacent to the road we were talking about before. Okay. We just have seen in the previous slide that till meters can be employed to monitor rock slopes, but they can also be used for the monitoring of soil slopes. You can see here some images. They all correspond to the same site. In this case, in particular, there is this sensor is a combination of laser distance meter and till meter. Both sensors in one data logger. So with this solution, these sensors were attached onto a pole that was stuck into the soil. And the idea was to monitor this railway embankment, soil embankment, because there were some drainage issues in this case. I'm done from my side. I will hand over the presentation now to Víctor. Thank you for your attention. Okay.
Thanks, Àngela. So thank you. I want to thanks for inviting us to do this, to collaborate with this webinar. Now, after seeing the presentation of my colleague Àngela, I will be entering more in detail in the tilt meter, in the kinds of tilt meter and the principles of the tilt meter we are using. So first of all, I will mention very fast the different technologies we have when we are talking about tilt meters related with the geotechnical monitoring or the structural monitoring, there are different technologies. For example, we have a tilt meter based on a vibrating wire, which basically there is a mass which is perturbing the wire, and we are monitoring this wire to understand the frequency, and this frequency is related with the tilt of the device. Also, we can have the force balance ones that basically there is an accelerometer based on a spring connected to a mass, and the relationship between the movement of the mass is related to the tilt. Also, we have the electrolytical ones that are mainly are two electrodes, one positive, one negative, partly submerged into a electrolytic let's say electrolytical fluid, and depending on the tilt of the device, you will find the one of the electrodes is more submerged than the other. And at last, we have the MEMS. MEMS stands for microelectromechanical systems. These devices have become very popular in the geotechnical monitoring devices because they are offering very good performance, and they are cheaper than, for example, the force balance ones. Okay. And they are becoming very popular not only for geotechnical applications, but for any application. They are present in our smartphone. They are present in the navigation system of the planes. So, and the technology is basically consists on a series of fixed plates that are combined with springs, and depending on the position of these springs, you are generating different currents in between the plates, and this is transduced into acceleration. Okay. Our tilt device that Àngela showed before, the Tilt 90X, it's based on this technology. It is a 2-in-1 device because it contains the sensor itself, and also it is a data logger that it's capable to transmit data into the network. Okay. And it's suitable for geotechnical and structural applications. And it is constituted to perform static measurements. It's from 30 seconds to 1 day. You have this periodic sampling, and you are transmitting in a periodic basis the results through the network. Okay, to say that the sampling, for example, each hour, this device can reach lives for up to 10 years or more. Okay, so when we are talking about a MEMS accelerometer, how it works. So basically, the triaxial MEMS accelerometer is capturing acceleration in the 3 orthogonal axes. Okay, and this acceleration can be split in 2 components. We have on the one hand the AC that it's a component, and the DC, which is related with the tilt component. Okay, if we have still in horizontal position the device, we can see the contribution of the gravity, and all this contribution, it's going to be on the vertical component. Okay. Meanwhile, the DC for the horizontal components X and Y, it's going to be null. What happens if we are rotating this device that was originally in an horizontal position? We had this all this contribution of the gravity in one axis. Now we are rotating the device, so this contribution is going to be spreading over the 3 axes. So if we are able to remove the AC component or the vibration component, we can find 3 accelerations that can be related with the gravity value, and relating them with the trigonometrical equations, we can retrieve the tilt of the device. Moreover, if we are considering that we start from a rotated position, we can consider this rotated position as our 0 reading, and from them we can see differential rotations in the 3 axes. Okay. This enables us to use the device at any installation position that we want, because With this reading, we are able to install the device at any direction and use this starting reading as our zero reading. So we can deploy the device on a roof, on a wall, over any surface. And this is the so-called auto leveling of the MEMS sensors. Okay. So two considerations about the triaxial, let's say the triaxial MEMS accelerometer to compute tilt. Usually, sometimes you are seeing that these kind of devices are called triaxial tilt meters. Well, this is not entirely true because we are obtaining three angles, okay, but these three angles are not independent. Okay, only two of these angles are independent. Those angles that are let's say towards the horizontal. Why? Because we have symmetry towards the G vector. So this kind of in the picture of the right, we can see that a rotation over the vertical axis, it's not going to be changing the behavior of the lecture on the sensor. So we are not detecting this kind of rotation. We are detecting rotation in the other angles, in the pitch and the roll. Okay, and we can transfer this in two independent angles in any position of the device into the A and B angles, usually used in geotechnical applications that are related to the horizontal plane. Another consideration is the resolution of the measurements. The MEMS accelerometers have sensor accuracy, which is constant along all the dynamic range. It's not really affecting if you are reading small accelerations or bigger accelerations. But as we are transforming this lecture into a angle or a tilt, we're using the sinus function, and in some way the accuracy of the angle, it's varying as the sin slope, and this is the cosinus function. Okay, so we will be more accurate at small angles, measuring tilts, and less accurate when we are near 90 degrees. So discussing of the data quality and the errors involved in this kind of sensors, the first one should be the calibration, but calibration, it's something that it's solved in factory during the manufacturing of the sensors. So sensors are calibrated when they are going to the market, let's say, and notwithstanding, several errors remain on data. Okay, one of them is the thermal dependence. Okay, MEMS response in temperature is not still is dependent on the temperature of the device. So we will see different results if we are measuring at different temperatures for the same position. Okay, so at this point we have to be cautious, because one part of the thermal effects, those related with the structural behavior, for example, the thermal effects on a bridge, for example, we are interested in those effects. So this is data. But on the other hand, these thermal effects on the sensor itself and on the anchor are not data, they are error. So how could we identify these errors? Is method is to have a long baseline in advance to the project or in advance to identify which is the response of the sensor. Nevertheless, this error is small. If we see the range, it's in the order of the millesimal part of the degree. So probably changes we are looking for are higher than this. And on the other hand, we have the vibration influence. We say that we have the DC and the AC mixed, and the component of the vibration must be removed. Nevertheless, when we are measuring in high vibration environments, for example, if we are measuring just when a train is passing by a railway near the slope or whatever, we are recording also this vibration. And to remove this vibration, we have two options. One is to filter the high frequency components, okay? But for this, we need a long trace, and it's not very friendly to perform on the air or on the running. And on the other hand, we can compute the mean and have the standard deviation, and we can do this on the air, and it can explain us the quality of the measurement. Here, for example, on the right, we have a low vibration measurement. You can see that depending on the exact point you pick up the sample, it can be different. But on the left, that is a high vibration environment, this difference is bigger. So a good understanding on this is to capture the mean of several samples and consider the standard deviation to understand this effect. And this is all regarding the tilt meter and its principles and transducing. And now we are showing our event detection solution. What is it? So our event detection solution is a key element on an early warning system. Okay, it can be in addition to others like cameras or other kind of sensors that are reporting near real-time or real-time information. But in this case, this key component is based on the usage of detection of events that are occurring in our asset. Okay, that can be slope instability, and we want to report this occurrence as fast as possible. In this case, we are talking about near real time. That means less than 5 seconds. Okay, so the idea here is to send an immediate alarm to a early warning system that it's able to take decisions or informed actions, okay, based on the alerts or information that we are transferring with this system. Okay, and how works for the event detection solution for Worldsensing? It works like this. It's the same that the Àngela presented before with the different networks we have. But in this case, we are using the same box of the tilt meter that it's used in the static acquisition. But in this case, it's operating under the so-called event detection mode. So what is it? So this mode is just, instead of having our node or our sensor reporting information in a static way, it's an hour or it's 2 hours, we are changing this behavior and we are migrating to the dynamic. This means we are sampling continuously at 3.9 Hz. So we are continuously looking for the tilt vector. So at this point, we can configure thresholds, absolute thresholds in different axes, okay, one upper and one lower, and at any range of the scale. So what happens when any sample it's breaking the threshold? We enter what we call the alert state. What it means? It means that an immediate alert message is sent, and moreover, the periodic reporting rate is increased. Okay, so for example, if we were reporting lectures each hour, and the broken is broken, and we are entering the alert state, we're gonna transmit each 30 seconds, for example. Okay, so we are changing this rate. And here is a picture on how the system operates. It's illustrative for, we are starting from the left. So we are in the normal state. We are below the threshold, okay? So we are computing each hour, each 2 hours in a static way. We are transmitting a baseline of our structure, okay? But what happens when a single tilt sample it's reaching the threshold? So we are entering the alert state. We are increasing the sampling rate, and the most important, we are transmitting immediately an alert, okay? And we can see here the number 2 is the alert, this is immediate. Later, there is another message that is transmitting information about this exceedance of the threshold. For example, the axis, the exact tilt that exceeded the threshold, etc. And at the end, if we at any time are below the threshold again for a while, for a stoppage time, we are returning to the normal behavior of the device. So we are returning to the normal periodical readings and the normal. So this is more or less how works the system. Take into account that this is a one-axis representation and only for the upper threshold. Okay, so it's not the entire system, but it's representative. So now what we can do is to see a live demo, okay, of the solution. For this demo, we are using a box of the Tilt 90X, okay, that is operating this event detection mode, okay. This is configured to report information each half an hour, but thresholds have been configured in all horizontal axes at -10 degrees and +10 degrees. So we're gonna force an alert. We will see the message incoming, and we're gonna change the reporting period into the 30 seconds. Okay, these messages via radio are going to a gateway, which is deployed on the roof of the building where we are, and then we are pushing these messages through MQTT into a broker, MQTT broker. So these messages are, let's say, gathered through the free software that we are using to simulate the consultant's software, early warning software, where alarms and other components of the early warning system could be. Okay, so we will subscribe this MQTT broker and prompt the messages which are arriving. So I will change now to this screen, okay, in which we are here. We have this this device, okay, prepared, configure it as told before. I will refresh this this window, okay, and now what we can do is to perform a flip into the X direction, okay. I will flip in this direction, and we're gonna see the alert in real time, let's say, as it was the software, okay. So I perform the flip greater than 10 seconds, and here it appears the alert message. This alert message, there is a lot of fields here explaining which node reported, which kind of axis has been broken, which threshold, and explains a lot of things, but does not include the absolute data of the event. This is because this information is not critical, and it comes with a message that has arrived just now. Okay, what happened if now we are in an alert state and we are supposed to be reporting each 30 seconds, but I can flip again into the I direction? So as another threshold is broken, we are receiving another message for the I component. Okay, and now it's 30 seconds, a message with a report. This message, which is basically periodic reading, it's appearing, but in rate of 30 seconds instead of the half an hour we had before. And what happened if we return to the original position after a stoppage time, which is more or less 1 minute? It's gonna be returning to the original state and reporting it half an hour. Okay, this is okay. So after this demo, I will explain briefly, and for to finish our presentation, a use case, an actual case that it was deployed on Brazil. Okay, an actual deployment on Brazil. This is based on tailing dams, also called tailing storage facilities. Okay, for those that are not familiar with this structure, it is mainly an earth-filled embankment that is present on mines, and it is used to store the mining non-profitable materials. So the stability of these structures along all the life cycle, because these structures are not static, let's say, or see they have a dynamic growth when more materials are pumped, mixed with water, and this structure is growing. So in all the phases of the tailing dam life cycle, the stability of the slope it's a critical thing to monitor, because failure on these structures can lead to safety critical fatalities, and also to environmental fatalities, so or problems. So in this case, we are talking about a project in 17 critical dam sections, property of Mosaic. that are distributed along 5 mining complexes. Okay. To this, a consultant was hired to monitor, and previous instrumentation was active. So they had piezometers, water level sensors in place inclinometers, as well as total stations and prisms, and interferometric radar and cameras. Okay, but there was a requirement for near real-time surface displacement monitoring. Okay, in this frame, on December 2020, with the help of Tetra Tech, which is the consultant who run the project, 120 Tilt 90X devices operating the event detection mode were deployed. And to complete the event detection solution, CMT Cloud platform operating a multi-gateway park was present there. This granted connectivity and redundancy for all the critical areas. Okay, and the software from the consultant was fed with data and eventual alerts with a latency less than 5 seconds. The consultant was also in charge to define the exact thresholds they want to see, and several tests were done in field to assure that the system was responding. Okay, the data is nowadays ongoing, and recording is ongoing nowadays, and it can be seen from the graph on the right hand that after a few days of let's say stabilization of the concrete boxes in which the sensors was installed, the system has remained very stable with displacements less than 1 millimeter. Here they are transforming the tilt of different points in distance. Okay, and from the test at the bottom, it can be seen that in this graph we can see how they perform a test. They just shake one of the devices like we did here to test the response system time was okay. So here I finished my presentation. Now, if you like, we can move on into the Q&A session. Okay, here, just in case you have our emails, Àngela's and mine.